Hello everyone, my name is Han Shenxiang and this is question 1 of homework 10 in the probability and stochastic process course. And in this question, we want to recall the lecture notes and collect the definition of the photo 7 process and recall some property of them, like some probability mass or density function and the mean expect value, the autocorrelation, and the autocovariance of this process. And at first, we want to recall the boson process. The boson process, we could define it as the like the we weight the bus, the number of the bus in the interval Ti from the T1, T2, the probability of it, the n is equals to T1, T2 is equals to K. Oh, sorry, there is more equal. And the probability is equals to e to the power of minus lambda t and the lambda t to the power of k over k inch. And it is the definition of the boson process, and there is some property of it if the interval t1, t2 and the interval t3, t4 are not overlapping, so the random n t1, t2, the n t3, t4 is not are independent. And for the third property, at the moment t, there is no more than one boson point. Is obvious. We could write a graph. The xt in the t time is the boson process, and for only the time, one time is only the 1 point, like this. And for the we could compute the probability mass function. The mass function is also equals to the definition is the probability of xt is equals to k is equals to this function as euro, and the mean, the expect value of xt is equals to lambda t, and the autocorrelation t1, t2 is equals to lambda to the power of 2 times t1, t2, and plus the lambda times the mean of the t1 or t2, and the autocovariance of t1, t2 is equals to lambda times the mean t1, t2. And for this function, this process, the boson process, the mean is lambda t, and it is the linear function of the t. It means, like we defined before, we weight bus, the more time we wait, the expect value number of bus is larger, so there will be more bus we could wait. And the autocorrelation function is contains the mean lambda mean t1, t2. It is the property of the independent increment, so we could use it to define the second process, the boson increment process. And it is defined of the increment of the boson process like the time shift. The difference of time shift is this is the boson increment process, and the xt is also the boson process. And for this process, we could compute the mass function, the probability of yt is equals to n over the epsilon is equals to e to the power of minus lambda epsilon times the lambda epsilon to the power of n over the n, and it is just different from n to k and the epsilon to t because it is the increment process, and the expected value of it is lambda is not in relation with the t because it's just the increment, and the autocorrelation of t1 and t2 is equals to lambda to the power of 2 when the t1 minus t2, the absolute of it is bigger or equals to epsilon, and when it's smaller to epsilon is equals to the lambda to the power of 2 plus the lambda over the epsilon minus lambda times the absolute of t1 minus t2 over the epsilon to the power of 2. And the autocovariance t1 t2 is equals to also the lambda it is 0 when the t1 minus t2 absolute is bigger or equal to epsilon, and when it's smaller to epsilon is equals to lambda to the over, it is this part. It is the autocovariance, and for the Poisson increment process, it is introduced to prepare us to define the Poisson impulse process. It is just one way to define the Poisson impulse process, and we could now find this expression and it is a triangle area with lambda, and it is independent of epsilon. So when the epsilon goes to 0, and the triangle will become an impulse with area of lambda, so it will become the next process with the point impulse process. And for this process, the definition of it is zt is equals to derivative of xt to dt. The xt is the Poisson process, and the graph of it is just like some impulse in the t-axis, some impulse, and when the ti, and there is no mass function of this, but we could compute the expected value of the zt is also the lambda because it is the derivative of the t of xt, and the autocovariance rt1 t2 is equals to lambda to the power of 2 and plus lambda delta t1 minus t2, and the autocorrelation covariance is equals to lambda delta t1 minus t2. And for this part we could find it's very similar to we have been taught from professor about the white noise. So the zt, the expected value is lambda, so the zt minus lambda, the mean of this, it has the 0, and the autocorrelation of it r t1 t2 is equals to this part, so it is equals to the white noise. And in the real world there are some short noise, we also could use this to definition 8. It's like this, some white noise. And we could also define it as the output of the linear time invariant system with the impulse response, and the input was the boson impulse process. For next, we want to talk about the semi-random telegraph signal. And for this process is also based on the boson point, and the boson process T1, T2 equals to K is this function we write before. And we will do more about it if the xt is equals to 1 or minus 1. The k is even, it is 1, and the k is odd, it will be minus 1, and in the time 0 to t. And we could define it as the semi-random telephone signal, and the mass function of it, the probability of xt equals to 1 is equals to the we have computed in during the class, use the cosine ht and the cosine sine ht equals to minus 1 is in this expression. And the expect value of it is equals to 8, this one, and the autocorrelation of T1 and T2 is equals to the T1 minus T2, the absolute, and the autocovariance of it is equals to the autocorrelation minus the T1 plus T2, and for this function is the autocovariance. And for this semi-random telegraph signal, the p xt is equals to 1 is not the 1/2, because we start with the plus 1, not the 0. So it will be the probability of the 1 is will be should be a little higher than the 1/2, and when the t goes to infinite, and it will be very very similar to the 1/2. And the expect value of it will go to 0. So it and the random the autocorrelation of it will goes to 0 when the T1 minus the tau is goes to infinite, and it will match the common signs when the T1 and the T2 are far away. There will be less relation between these 2 points of xt1 and xt2. That's right. And for the next we will introduce the random telegraph signal. It's not the semi-random, and we could define it, and yt is equals to a times xt, and the probability of a equals to 1 is equals to probability of a equals to minus 1 is half and the xt is a semi-random telephone signal, and it is independent of xt, and we could do the mass function. The probability of yt is equals to 1 or equals to minus 1 is the A is equals to the 1 over 2, and the expected value of it yt is equals to 0. It's obvious. And the autocorrelation, the rt1 t2 is also is equals to the xt is equals to e to the power of 2 times lambda times the t1 minus t2 absolute, but the autocovariance is different because of the a the expand value is equals to the autocorrelation because the expand value of it is equals to 0. And for this process, we could know that the probability of yt 1 or minus 1 is equals to half, and we will guess that the yt may be the strict sense stationary process because of the expected value of yt is equals to 0. It's a constant. And for the sixth process is the random walk. We could define it. At first, we toss the corn n times and n times, and the k is the number of the head, and we could define it the xnt is equals to ks minus n minus k. The n minus k is the number of the tail, is equals to 2 times k minus n s is the xnt. And we could now compute the probability mass function. The probability of xt is equals to xnt equals to rs is equals to two condition, the n plus r to the over 2. It is for the nt to n plus 1t. It's in the 1 aperic. And the mean of it, the expected value of xt is equals to 0 because it's n times, the corn have the equal probability of head and tail. And the autocorrelation of rt1 t2 is equals to mean m s to the power of 2, and the autocovariance t1 t2 is equals to the autocorrelation. And we could know the probability mass. There is two conditions, and we could guess when the n goes to infinite, and we will have the Gaussian density. The autocorrelation function contains the mean. It's mean t1 t2, which it is from the probability, the property of independent increment, like the boson increment process. So we will know about the next process, Wiener process. The Wiener process is the limit. We will define it and limit when the r goes to n, and the t s to the power of 2 over t goes to alpha, and the n goes to infinite about the xt, and the xt is the random walk. It's a Wiener process, and the density function, we just know the first order density function, the f omega t is equals to the r pi alpha t 1/8 and times e to the it's like a Gaussian function, and the expected value of it is equals to 0, and the relation autocorrelation is equals to mean t1 t2 times alpha, and autocovariance is equal to autocorrelation is also this function. And for this process, at first we could know the W0 is equals to 0, and the winner process is also an independent increment process when for the different W t is just like because of the Gaussian property, and the WT is a continuous path with a probability of 1, and it is continuous in T. It's obvious because it's Gaussian, like the graph of it is like this. This is a very it's a continuous graph, and this is a winner process. That's all. Thank you.